most of the time I want to dedicate, I want to spend actually working on our lab stuff. So typically in a lab, especially on an on-campus lab, standard MO, usually I'll do a little bit of a chalk talk, just to kind of frame the lab a little bit, make sure you guys are pointing in the right direction, give you any information maybe that you might need in order to do the actual lab itself. For the first week, and I just posted them on Connect. So you should see them posting on Connect here in a few minutes. Is the metrics lab. That's typically always the first lab we do in Bio 111, the metrics lab. That usually comes with our first day in the lab, our first lab day. And we usually do this all as one lab. Now in Connect, it's got it broken up into 4 separate virtual labs. So when you do the virtual labs in Connect, one of the things to be aware of is to make sure that each of the required pieces that they're asking of you are done accurately. Oftentimes what will happen in Connect in the virtual labs is it'll ask you to measure out, say, 1 milliliter of something using a graduated cylinder, for instance. And if you don't measure it out correctly, or if you don't read the actual volume correctly, and you put in a number, then it'll be a wrong number and it won't let you advance. And so a lot of times you're kind of stuck and it won't let you advance. And you're like, well, wait a minute, how do I get out of this? And a lot of times it's because the input you put in was not correct. And it's oftentimes not uncommon for that particular question in the virtual lab to get students stuck a little bit. And essentially, it's usually about reading the meniscus. So the meniscus is that kind of little, it's the surface of the water, but you notice the surface of the water has a little bit of a pucker to it. And so you always read the bottom of the meniscus, not the top. So the bottom of the actual water level. So that's all the piece to it that you always read. And if you don't read the bottom of it, then you'll put in the wrong number and then you won't be able to advance. 9 times out of 10, it's something like that when you're getting stuck with these virtual labs. If you do get stuck, let me know. Oftentimes, I won't be able to do it myself, but if you do a couple of things, take a screenshot of what you're seeing or where you're stuck. Sometimes I can figure out what's going on and kind of help get you unstuck if I see the screenshot of where you are stuck. Or if you set up a WebEx with me and I could let you screen share and I can see where it is that you're getting stuck. Oftentimes we'll kind of get you unstuck, but 9 times out of 10, it's usually some sort of an input. Maybe some sort of a measure was read incorrectly, and it needs that to be correct in order to move forward. That's usually what it is. Like I said, you should be able to see those virtual labs now. And so go ahead and play around with those and see what they look like. Give me any ideas, feedback, anything like that if you guys get stuck. So let me know. Okay. Can you guys see the screen? Okay.
Looks blank right now, but I see the screen.
Yeah, so it should be a blank slide. It's a PowerPoint slide, so I'm just going to write all over this, basically. So good question, Hannah. The lab coats, there's not a specific requirement. Pretty much any lab coat will work. The goggles do need to be sealed to the face. Lab coats do at least need to go down to the mid-thigh, as opposed to one of the shorter coats, which are kind of like they go to the waist. We typically want them to go a little bit beyond the waist. They don't have to go dragging all over the ground, but they need to be at least like mid-thigh-ish or so, which is where your average coat is. Some of you may have like little scrub coats, which are waist length. Preferably, we want them to go a little bit longer than that. But for the most part, a standard lab coat should be sufficient, which usually terminates somewhere between the hip and the knee. But the goggles need to be against the face. So if they leave a nice little mark around your eyes, that charming little mark to let everybody know you've been in a lab for a little while, that would be perfect. Because those will seal to the face. They have, you want them to seal to the face. So you can't have glasses. Glasses are open on the edges. They actually have to seal to the face for splash contamination to be able to qualify for splash resistance. Okay. Any other questions before we get ourselves started on the chalk top? Okay. Well, I guess no news is good news. So let's go ahead and get started. So this first lab is about the metric system, and there's a couple of things that we want to pull out of the metric system. So just as a quick temperature check, how many of you are familiar with the metric system?
Yes.
So we got a definite, solid, confident yes. How many of you, anybody else?
Somewhat.
So somewhere in between, okay. Has is anybody kind of like, okay, I no idea about the metric system at all? Nobody wants to own that one, right? So the metric system is a system of measurement. And so the reason why it's important is because we've historically, if you look at the history of measurement, there's always been a little bit of a problematic history with measurement. And it's the system of measurement that is used in science. So everything we do in science is metric. And it's what most of the world uses, actually. Europe, everybody else uses metric system. Pretty much the only place where the English system is used or the imperial system is used is pretty much in the Commonwealth, the British Commonwealth, of which we were a member until we rebelled. And so now we still use the English system. So really, when you take a look at the systems of measurement, there's really a couple of major things that you want to measure. So first of all, one of the things you want to measure is length. And that's a pretty common one. A couple of other things you want to measure as well is mass. So that's another common one we want to measure. So volume, we like to measure volume. That's a good one. And of course, temperature. Those are some the four main parameters that we want to measure. Now, here is the problem with measurement. And I want to use length as my example. So if we were to take a look at length, how many different types of length are there? Just either send in through chat or mic in, like just give me some measurement of length, whatever it is. First thing,
Centimeters.
so that would be metric. So I'm looking for an English version.
Inches.
Okay, I got inches. What else? Did any other one come up into somebody's mind? Feet, miles. Any football fans?
Yards.
Yeah, right. Yards. So all of these are examples of the problem with the English system. Think about this for a second. An inch. I mean, it's roughly about the size of your thumbnail, right? I mean, not quite. Depends on how big your hands are. But basically, we're all pretty much comfortable with the size of an inch, right? How many of you guys have a ruler at home? Or a tape measure? So we take a look at an inch and we say, okay, that is a measure of which one of these parameters? It's a measure of length, right? Distance. And then if we have 12 of those, what do we have? Yeah, a foot, right? And how about a mile? How many feet are in a mile? Denverites, right? 5280. So if you have 5280 feet, then we call it a mile. How many feet are in a yard? Yeah, 3-ish, right? How many inches are in a yard? Yeah, 36-ish, right? Thereabouts. So here's the problem, right? We have an inch, which is roughly about the thickness of our thumbnail, roughly, right? We have 12 of those, and we call it, do we call it 12 inches? No, we call it a foot. We have 5,280 of those. Do we call it 5,280 feet? No, we call it a mile, right? And so the problem is you've got all, what are these all measuring? What do these all have in common? These are all measuring what?
Length.
Length, right? All of them, an inch, a foot, a yard, a mile, all measuring length, the same thing. Would you know that from just listening to my units? If I were to say, like, imagine you are an alien who just landed on planet Earth, you know nothing about anything about planet Earth, and I tell you inch, foot, yard, mile. Is there anything in those terms that would lead you to believe that we're measuring the exact same thing? You wouldn't have any idea whatsoever that they're even related at all, which is part of the problem with the English system. Not only that, but take a look at these wild units. I mean, where does 12 come from? I don't know. I mean, why isn't a foot 6 inches? Who made up the rule that it's 12 inches? I don't know. Probably what happened was somewhere back in the day, some king had a 12-inch foot, and we called that a foot. So now, because this king was so important that we don't even know him anymore, then we called that a foot. Back in the day, we had a devil of a problem with standardization of units. We wanted to build stuff, but the problem is, how do you measure it off? Right? Do you use the foot? I don't know. Whose foot do you use? Do you use the contractor's foot? Do you use, the people who are working, right? The slave help or whatever who are actually building, do you use their feet? Do you use the king's foot? What if the king's foot got a little itty bitty foot? I mean, honestly, think about this for a second. Does any pharaoh of Egypt want to be known as the dude with the little feet? I mean, is that why he's building the mammoth pyramid? No, no pharaoh in their right mind wants to be known as the dude with the little anything, right? So you don't want to use that. And so the question is, whose foot do you use? Right. And so then also the problem is, I mean, a foot can be problematic. I mean, like for instance, me, I've got a fairly smallish foot for a guy. I mean, I wear an 8.5, which is not all that great, all that big. Right. So, but some people will have big feet, 12, 13 size shoe, 13 inches. So if they go and they use their foot to build something, they're building a pretty big house. If I build one, it's pretty small. So there's a problem there, right? So then how do you determine and standardize distances? Well, one of the things they used to come back up with at antiquity is the idea of called a cubit. And sometimes you'll read this in ancient literature, like in the Bible. Right, but basically the cubit was essentially the distance from your elbow to your wrist. And so those bones, radius and ulna, are typically bones that don't vary a lot in human culture, in human species. They do vary, but not as much as, say, the femur, which is where a lot of your height comes from. And so you would use this as a measure because it's fairly invariable. Now they had variations of this, the cubit idea, where they would say we're going to be measured by the king's cubit. So that's like the king's forearm of that day. But it was still pretty variable and too variable for a king who didn't want to be known as the little guy, right? And so there was always a struggle to standardize what this all looked like, and then along comes the English system, which is probably the most ridiculous system on the face of the planet. Because now you've got this little distance about the width of your thumbnail, and we call it an inch. Think about this one for a second. We're used to it in our culture because we're in an English system culture, but think about this for a second. Inch. What kind of a name is that? Right? I mean, think about this. If inch wasn't associated with measurement, is there even such a thing as an inch? I mean, what is that? Where do you come up with that? I mean, how do you come up with that as a word? Inch. It exists nowhere else in the English lexicon. What is an inch? And how do you come up with that? I mean, who was the dude who first came up with the term the inch? It's such a bizarre, such a random, just verbal foolishness of a term. Think about that for a second. How about a mile? Is there anywhere in the English language where mile actually has a real definition to it that is divorced of and separate from its use as a unit of length? I'm calling on you linguists, you linguistics experts. Yeah, I don't think so. Right? I mean, and then you have a yard. I mean, okay, so somebody's backyard. So is that a yard? Well, I don't know. My yard's a little bit bigger than 36 inches. So I'm not quite sure where the yard came from. Although I know some students do have some exposure to that. So some of these terms seem random and completely nonsensical. So here's what it's like. Imagine this. Let's do what people did back in the English system days. We have some length terms, right? We have an inch. We have 12 inches is a foot, right? We have roughly 3 feet-ish or so is a yard. So let's imagine we find ourselves in a scenario where we're actually making use of half a yard, like a lot. I mean, and so we're using it so much that we want to designate it as its own unit. So instead of calling it half a yard, which would make a lot of sense, instead, what do we call it? We're come up with some stupid, ridiculous, arbitrary, ridiculous name that doesn't exist in the English language, or better yet, that has a better definition somewhere else in the English language, and we call it a ham sandwich. So if you have half a yard, it's a ham sandwich. 2 ham sandwiches equals 1 yard. Now, am I being a little cynical? Yes, right? Because the English system is stupid. By the way, if you hate fractions, you have the English system to thank for that. So if you've ever built something, if you start getting a headache when you're trying to read off 3/64ths or 2/16ths, or, well, that's a quarter, but right, or like 3/16ths or 5/16ths or something like that, 3/8, 5/8. If you're having a headache doing that, you've got the English system to thank for that. So there's a problem, right? There's no standardization. There's no coherent, comprehensive pattern in terms of its nomenclature. So how does anybody have any hope whatsoever of understanding what fraction of a mile is a foot or vice versa, or how many inches in a foot, unless they grew up with that? Because there's nothing in the system itself that tells you how much you're dealing with, and that's a problem. Let's call half an inch an Uncle Larry. Why not? We liked Uncle Larry. Let's call it an Uncle Larry. Hey, could you measure that out to about 24 Uncle Larrys? Well, okay, I could do that. Right? I mean, it's completely arbitrary. Where does inch come from? I mean, where does any of these terms come from? Because they're not telling us any information in terms of what we're measuring, and that's the problem. Now, don't get me started on mass and volume, because there it gets even crazier, because we have ridiculous things like ounces. Oh, but wait. We don't have ounces. We've got fluid ounces, and then we've got dry ounces, right? Same term, completely different measurements, right? You can think, all you have to do is dive into English system measurements to realize just how dumb they are. And this is what we're stuck with. Okay. Now that we all know how I feel about that, let's go ahead and talk about the metric system. So the metric system is a system that's based on tens. First of all, that means that they've immediately made our math a lot easier. And not only that, but in the metric system, they center all of their units around what's called a base unit. Does anybody know what the base unit is for length?
Meters.
Yeah, it's the meter, right? Which would be the other side of the yardstick. Does anybody know what the base unit is for mass?
Gram.
Yeah, it's the gram. How about for volume? Yeah, liters. And then for temperature, the base unit is a little trickier. We have really 3 units that we use for the most part in temperature. There's degrees C, degrees Fahrenheit, and then there's Kelvin. So degrees Fahrenheit is the English system version of it. We're really the only ones who use that. We use it in like our body temperature, right? 98.6 degrees Fahrenheit. We use it in meteorology, right? But typically we're the only ones using it. What's the rest of the world using? Like if you go to Europe and you want to know what the weather is, what are you going to see? Which scale?
Celsius.
Yeah, right. And Celsius is kind of like the metric one. This is the one we use to measure in labs. So if we're measuring temperature in labs in science, we're usually using degrees Celsius. Now, Kelvin is actually technically the pure measure of temperature. It's what's called absolute temperature. That is to say that absolute temperature is essentially has a no negative scale to it. That is to say that the coldest you can get on the Kelvin scale is zero Kelvin. That's absolute zero. That's basically where all molecular motion stops. If you're at absolute zero, you are in serious trouble. Well, first of all, you were dead a long time ago. Let's just put it that way. But this is like the coldest of the cold of the cold of the cold. This is the coldest you can ever get in the universe is absolute zero. But the temperatures in Kelvin are all positive. And so that's the idea of Kelvin. That's why it's called the absolute temperature. So typically you only use Kelvin if you're in chemistry or physics. Now, here's the problem. How big is a meter? For those of you familiar with the size of a meter. Like what's an easy comparison to compare it to? Okay, it's 100 centimeters. So for a yardstick, which is roughly about 3 feet, on the other side is a meter. So here's the problem. Is a cell on the meter scale? So if you wanted to measure a cell, would you refer to a cell as being in meters? No, right? Because if you were to explain a cell in terms of meters, the size of a cell would be like 0.000000000000000000000 meters, right? It'd be really tiny. And so that's not helpful because nobody wants to write down that many zeros every time they want to talk about the size of a cell. Not only that, but if you're going from here to, say, for instance, China, would you talk about the number of meters that you flew? No. What would you be talking about? You'd be talking about miles, right? But then in terms of the metric equivalent, you'd be talking about kilometers, probably, right? So that gets us to this idea of scaling. So everything is based on tens, but the nice thing about the metric system is instead of calling, some bigger measure, a ham sandwich or an Uncle Larry that has no interest, no information to it, what the metric system does is it basically scales the measure. So basically it says, listen, we have our base unit, the meter, M. And so 1 meter is exactly, well, meter. And exponentially, we can express that as 10 to the 0. Now, what if we have the need to talk about more than 1 meter, like multiple, not just 2 meters, 3 meters, tens of thousands of meters, millions perhaps of meters? Are we going to always want to say we have 6.28468222 million meters? No, because that gets clumsy, right? So what they do is they use a prefix to scale their unit up. So they have a meter, but then they're going to say, let's use a prefix to scale it up. Let's talk about a kilometer, or km. This is going to be 1,000 meters, or 10 to the 3, 10 times 10 times 10. So instead of talking about thousands of meters, you can talk about single digits of kilometers. So instead of talking about, oh, I went, 3,246 meters, you could say, well, I want roughly 3.246 kilometers. So it gives you an easier number to deal with. Now, we can also continue to scale up with mega. A megameter, capital M, little m, is going to be 1 million meters, or 10 to the 6. If you continue going up, we can go to giga meters, big G, little m. This will be 1 billion meters, or 10 to the 9. What's after giga, all you computer folks? Anybody would know what's next on the list? So you go from mega to giga. What's the next one? We used to buy computers with gigabytes. Now we're looking at computers with what? Tera, right? Tera is the next prefix up. That's what that is. That's a prefix. So that is 10 to the 12 on up. However, this is getting bigger. In biology, we don't have the need to get bigger. right? Maybe if you're in astronomy and things like that, you get bigger like this. But in biology, we have to get smaller, right? We just said that the cell is like 0.00000000000000000 meters. So how do we get that smaller? Well, let's use prefixes. Now notice these are all lowercase now. So the next one is going to be, if we go down in size, we can use fractions of a meter. So a centimeter or a cm is basically 1/100th of a meter, or 10 to the minus 2. Notice the negative exponent basically means that it's smaller than 1. So 10 to the 0, there's a reason why I'm putting exponents here, and I'll show that to you in a second. But 10 to the 0, anything actually to the 0 is 1. So when it's a negative exponent, it just means it's smaller than 1. So it's 1 to 100. So basically writing 1 over 100 is the fractional way of writing. It's the same thing. It's the same exact number as 10 to the minus 2. Because 10 times 10 is 100. The negative number means that 100 is in the denominator. So it's 1 over 100. So this basically means it's 100th of a meter. Now we can go smaller to millimeter. This is little m, little m. Notice they're lowercase now. This is going to be 1,000th of a meter, or 10 to the minus 3. So on your metric ruler, typically you'll see inches on one side, you'll see centimeters on the other. The smaller lines within the centimeter, there's 10 of them in 1 centimeter, is the millimeter line. So we can get smaller than millimeters though. We can go to the micrometer, which is mu m. Now mu is a Greek letter. It looks like a little script U, so it's micro. That stands for micro. And this is going to be 1 millionth of a meter, or 10 to the minus 6. Then we can go nanometer, which is 1 billionth of a meter. Then after this, you can go picometer, which is 1 times 10 to the minus 12. You can go femtometer, which is 1 times 10 to the minus 15, and so forth. Typically, nanometers is where we need. Now, here's the problem. Generally, when we're looking at cell sizes and molecule sizes, this is the size range that they're in, the micro and nano range. Normally, our ability to measure is in this centi to milli range. So what that means is we have, really, really tiny things that we have to measure, and there's ways to do that we're not going to talk about now. But this is basically what the metric system does. Notice in all cases, you know exactly what you are measuring, because all of these terms have the word meter in it. That's the base unit. So you always know that you're measuring length. The prefix simply tells you what fraction or what scale that you're at. If you're at really tiny scale, centi, milli, micro, nano, or if you're at large scale, multiple meters, kilo, mega, giga, tera. And to answer Hannah's question, the sign for the micrometer is called a mu. It's a Greek letter. It looks like a little script U, like a little cursive U. So the nice thing about this is it basically does away with fractions. So no longer are you having to fuss with 5/8 and 3/8. Instead, what you're doing is you're using decimals. So the metric system trades out fractions for decimals. Now, here's one of the things you want to be able to do in the metric system, and that's conversions. Now, in conversions, many of you have, say, for instance, learned how to say, okay, I'm going to multiply by 1,000 or I'm going to divide by 1,000 to get my unit conversion. And that's fine if you want to do that. What I'm going to show you is kind of like a quick and dirty sort of a lab cheat, a quick fix, a quick way to convert between units very quickly, just in your head. And it's usually kind of like a lab cheat, something I use all the time in lab. And there's a two-step system. So here's what we're going to do. We're going to take 250 milliliters of a solution, and we're going to ask ourselves, how many liters is that? So there's basically two steps to be able to do this. A real quick and dirty way to do this, using the information that we have up here in our table. So the first one is, what we want to do is we want to figure out what the big units are, the big versus small units are, and what the big versus small numbers are. Always knowing that units are inversely related to the numbers. What do I mean by that? Well, let me walk you through it. Take a look at the ml, milliliters. Comparing it to liters, which one is the bigger unit? So liter, correct, is the big unit. That means the other one has to be the little unit. There's no other way. One's big, the other one is little. Now then, here's the deal. Now remember, the relationship is inversely related. The big number goes with the small unit. The small number goes with the big unit. So which number is 250 the big number of the two, or is it the smaller number of the two? It's the bigger one, right? Because milliliters is the small unit, so it's going to be paired up with the bigger number. That means this number here, the one you're going for, has to be smaller than 250. Does that make sense? They're inversely related. So if you've got your big unit, which liter is, it has to be paired up with the smaller number. So here's the question. How small? Well, basically, your decimal point is sitting right here after the 0. And so what you want to do is you want to move your decimal point the correct number of tens that exist between your units. So here's the question. So you want to move your decimal the correct number of tens between the units. How many tens are between milli and liter? Well, let's think about this. Liter is the base unit, yes? Yeah, 3. Exactly, right? So here's your liter. Milli is down here. So there's 3 tens. But now that you know you're moving the decimal point 3 times, the question, and this is what always trips students up. This is where a lot of students get messed up when they're moving the decimal around. They forget which way to move it. They move it to the wrong side. But here's the deal. If you know that your number has to be smaller than 250, then you move your decimal point 3 places in the direction to make this number smaller. That means I have to move this decimal to the left. So I move it once and it becomes 25. I move it twice, it becomes 2.5. I move it 3 times and it becomes 0.25. So it is smaller by exactly 3 movements of the decimal place. Why? Because there's 3 tens between milli and liter. So if you use that little quick cheat, then basically what's going to happen is you're never going to be able to make the mistake of moving in the wrong direction, because you know that small number goes with big units, big number goes with little units. And then you always know how many tens, because of the exponents, are between each of the prefixes. So you would be able to do this if I said take a number and convert it from kilometers down to nanometers. You'd be able to do that. A lot of moving of the decimal, but you'd be able to do that. Why? Because you know which of the units is big versus small. You know where the big versus the small number needs to be. And you know how many and what direction to move your decimal point. You do that quickly, and you could do these conversions quickly in your head. Or, as Rachel mentioned, if you preferred, you could divide by 1,000, and that's fine as well. So that's why I always tell students, there's no wrong way to do this. So if it's more comfortable for you to divide by 1,000 or multiply by 1,000, depending on which direction you're going, then by all means do it. If you like this system, by all means do it. It's just another way of doing it, a kind of a quick cheat way of doing it in your head when you're in lab and you're trying to do quick measurements and quick conversions in your head. Does that make sense? So that's the gist of the metric system. Any questions? Okay. So that's the end of the chalk talk. So normally, like in a face-to-face lab, like if we were doing our metric right now, basically I'd turn you guys loose to do your metric lab, which is basically just measuring a bunch of stuff out, you're measuring length, volume, mass, and temperature. So you're basically measuring all four parameters, using different types of tools, graduated cylinders, mass scales, yardsticks, things like that. And so that's basically what the gist of the lab would be, which is essentially what the virtual labs take you through. Okay, any questions?